Dear friends, today it's my delight to share a conversation with you with my co-author of Quantum Body, the book you've been hearing about and supporting. Uh, the book is co-authored by myself, Jack Tuszynski, and Brian Fertig. And actually, I want to share something exciting with you. Jack and I have decided that we will create a course through edX, which is a very big educational um, outfit, international, which supplies educational material and certification in many areas and disciplines. I've already done a course on the soul of leadership with them, which you will be seeing soon. And we spoke to the CEO of edX the other day, both Jack and I, and he proposed that we should do three courses, certification courses, one on quantum mechanics, one of quantum biology, and one on quantum consciousness. So QM, QB, and QC, quantum mechanics, quantum biology, and quantum consciousness. And so, what we're doing today is going to introduce to you some key concepts. And this conversation will be on YouTube. And depending on your feedback and whether you like this idea, we will actually create a very, very lengthy and a course which is based in science with all the scientific references, quizzes as needed in these three areas: quantum mechanics, quantum biology, and quantum consciousness. And the reason we're doing this, by the way, is twofold. One is over 40 years, my interest has been on understanding consciousness as the ontological primitive. Without consciousness, we can't even do quantum mechanics. So, all science happens in consciousness. All experiments are designed in consciousness. All theories are conceived in consciousness. All observations are made in consciousness. And science deals with models of reality. But I have always believed that fundamental reality is consciousness. And then I met Jack, who is actually a materialist. He's a physicalist, and he deals with quantum mechanics from the perspective of physical sciences. But as Jack and I started talking, and after we published the book, we realized that this is a much larger conversation because when we come to biology, you cannot separate a biological organism from mind, basically. Every biological organism has some rudimentary mind, if you will. If by mind we mean sensory processing, motor activity, response to the environment, making choices. There are levels of mind. In our case, it goes to the level of insight and intuition and creativity and higher consciousness and aspirations and longings and dreams and memories. And no model of reality that excludes mind is a complete model. So if quantum mechanics does not include mind, then it's an incomplete model because reality contains mind. We are having this conversation because of mind. Okay, so we think quantum mind or quantum consciousness is a legitimate area of study, and quantum biology, because if our biology is part of the material world, and our biology is also an expression of quantum mechanics, then we should be addressing quantum biology, notwithstanding that the simplicity of, say, the double slit experiment may not apply totally to all the things that are happening in our biology. So with that introduction, I first want to welcome Jack with this idea that we're going to do this course. Jack, what do you think so far? It's a good idea.
Yes. May I say a few things
Yeah.
in terms of kind of a historical background to what you were saying? From my personal perspective, as you say, I'm a physicist by training, and I've done a lot of different research in various areas of physics. More recently, as you mentioned, in quantum biology. I've always been interested in biology as a physicist, but biology only recently, in the last 2 decades or so, became quantifiable to a degree that is amenable to physical interrogation, so to speak. And more recently, I got interested in consciousness, and there is a story to that. In 1991, there was a conference I co-organized with some very eminent scientists, and it was sponsored, believe it or not, by NATO, this organization that is now, of course, very strong and growing stronger. But at that time, it was interested in research and science and things of this nature. So the conference was called "What is Life?" And it took place in Tucson, Arizona, and the other co-organizers were Arthur Winfrey, Stuart Hameroff, Steen Rasmussen, myself, and that conference was amazing. And it ended with Stuart Hameroff challenging the audience to organize the next conference under the title, "What is Consciousness?" We haven't, we at that time, we were not able to answer the main question, what is life? But I think we jumped into what is consciousness. And subsequent years saw the emergence of Toward the Science of Consciousness conferences. You took part in many of them, I'm sure, and they continue. And that I think is the beginning of a conversation from my perspective, which is ongoing, but I think it requires probably a more open attitude than it has been so far, by questioning, perhaps delving deeper into the issues of physics, quantum physics, classical physics, what it means for biology, and what it means for the neuroscience, for the study of the human mind. And I also want to mention that out of this conference came out a very interesting book by Alwyn Scott, I'm sorry, the late Alwyn Scott, who was a great neuroscientist and mathematician, polymath. The book is Stairway to the Mind. I really recommend this book because it touches on many points that we'll be probably discussing in these.
What's it called again?
Stairway to the Mind.
Stairway to the Mind. Okay.
Yes, because this is where I think a lot of problems are rooted, and not quite all of them are even properly addressed or understood. He talks about the hierarchy of organization in the universe and how different hierarchies have their own rules, and how connecting between the hierarchies is the key problem that we are still facing. So anyway, that's just my...
I read the book, but obviously Stairway to the Mind is written by a mind.
Yes.
Right.
Indeed. Indeed.
Okay. So, to start this conversation, I have this little summary of what you sent me, and I'm going to use it. But I think, because we are creating this course for not only students, scientists, people in the area of technology, but also people who are interested in philosophy, in the deeper questions about life and consciousness. I thought what I'd do is, as a start, before we go to your first item, the problems with quantum mechanics, before we go that, let me outline in very brief, less than 5 minutes, the most important principles of quantum mechanics, so that we actually get agreement on that between you and me. And then once we get agreement, then we go on to the next phase. So, I've been looking at this area. In all honesty, I'm not a quantum physicist. I'm a physician. My interest in mind-body medicine began in the 70s when I was working with Seymour Reichlen, who was then the president of the Endocrine Society. And we were looking at the molecules of emotion or what we call the molecules of emotion, then serotonin, dopamine, oxytocin, opiates, and the receptors to them. One of my colleagues, Candice Pert, discovered the opioid receptor, and I got interested in the interface between consciousness and biology. And, because there was obviously a molecular substrate for wherever a thought goes, a molecule follows. And the molecules happen to have receptors in all the cells of the body, including the immune cells. And not only did the immune cells have receptors, but they communicated with neurons. So there was a back and forth, and it became obvious that to some of us that the mind could not be localized in the brain, because it seemed like the whole body was acting as a mind. And then later that led to discussions in consciousness. I've been going to the conferences that Stuart Hameroff has been organized, and I hope to see you there again this year. I'm doing a plenary on consciousness as solving the hard problem of consciousness. And as usual, we'll see a lot of debate on that. But here are the foundational principles of quantum mechanics that I think most people will agree on. Number one, wave-particle duality. So we forget the classic wave or particle picture. In the quantum world, things like electrons can act like both particles and waves simultaneously. This counterintuitive concept helps explain how basically light works at a fundamental level and how other particles work. Particles have location in space and time. They have units of mass and energy. Waves have no location in space-time and do not have units of mass and energy. This is a revolutionary discovery. The second principle of quantum mechanics is superposition. Before you measure a quantum object, it can exist in multiple states at the same time. Imagine a coin being heads up and tails until you actually flip it. The fuzziness is essential for understanding many quantum phenomena. So as we go deeper and deeper into quantum phenomena, it becomes the demarcation between what we call matter or things starts to become kind of fuzzy. It's not things anymore. It's fuzzy clouds of probability or possibility. The third principle that everybody agrees on is the uncertainty principle, which says there's a fundamental limit to how precisely you can know both the position and momentum of a particle at the same time. The more accurately you know one, the less certain you can be about the other. And this has profound implications for experiments and how we view reality. The next principle is quantization. Energy, momentum, and other properties come in discrete packets called quanta. Imagine stairs instead of a ramp. Things can only exist at a certain specific level and not anywhere in between. This explains why atoms have stable energy states and why light comes in specific colors. And then there are other foundational principles, probabilities and wave functions. We can't predict the exact outcome of a quantum event, but we can use wave functions to calculate the probability of different results. These wave functions are mathematical objects that encode everything we know about the system. So Schrodinger's wave function, is it physical, is it non-physical, is still being debated. And then there are other concepts, measurement and observer effect. The act of measuring a quantum system affects its state. This means the observer is not separate from the observed, and that our interaction with the world at this level fundamentally changes things. The observer and observed are part of a unified process, let's say a system. Then there's entanglement. This mind-bending concept describes a situation where two particles become linked even if separated by vast distances. What happens to one instantly affects the other regardless of space and time. So these are, I think, principles that are agreed upon. But then, we are going to delve, as you know, in this course into quantum biology and quantum consciousness. And when you and I had this conversation, you sent me this wonderful note. And I thought today we would just deal with the problems with quantum mechanics as you outline them in this little note to me. So let's start with that right away. First of all, any comments on the foundational principles that I mentioned?
Well, you outlined it very well. I think this is a good summary. There also, I would say, some of these concepts I would call gifts of quantum mechanics to the sciences in general, because that these ideas change the world around us, how we perceive it, how physicists and scientists in general think about the world, the material world. And indeterminism is a revolutionary idea, I think, because I want to go back for a second to the prevailing paradigm, going back to Simon de Laplace, who said that give me the initial conditions of all the particles in the universe, I'll predict the future. And quantum mechanics dealt a blow to this thinking that even a single particle cannot be predicted. Its evolution cannot be predicted, let alone the entire universe. So that puts everything on its head. So that's only one of those things. The other, of course, you mentioned the quantization, that is discrete energy levels and discrete values of various physical properties. And I think there is one more which I would like to add to this list is the concept of tunneling. And that's a consequence of probabilities, right? And tunneling allows for the events to occur in spite of seemingly insufficient energy levels. So thinking about, let's say, throwing a ball towards a ball, a ping pong ball, or whatever ball you can think about, towards a brick wall, and you would expect it to bounce back to you. But in quantum mechanics, actually, there is a probability it'll penetrate through the wall and emerge on the other side of the wall. So these are paradoxical things, and yet these things found immense technological applications, including semiconductors, electronics. All of these things work on the principle of tunneling, and also in biology. We'll come back to it later, but tunneling has been seen to occur in biological systems, in the functioning of the electron transfer chains in mitochondria, for example. So it's very important. It's not an incidental thing. And maybe one last comment, historical, because I like to talk about the history of science as much as science itself. So physics underwent this quantum revolution about 124 years ago, to be precise, and it was based on just a few observations. A few observations that were very difficult, if not impossible, to explain using traditional classical thinking. And I think in biology today, we have a similar situation where there are a few quirky things that are hard to explain using biochemistry, cell biology, things like, for example, partly explained photosynthesis. How is it that it's so efficient? How is it that our organism is totally coherent, that how is it that we perceive the world as one? And there's a few things of this nature. And so classical science has great difficulty answering that. And I think we will try to shed light on it. So biology and let's say consciousness studies, I think, are at a point in their evolution, which is to me analogous to physics 124 years ago.
That's a great summary. And before we go ahead, I have two questions actually. One on Laplace. I think he communicated with someone, was it the Pope or something, about this idea that if you give me the initial conditions, I can predict everything in the universe. And somebody asked him, what about God or something? And his response is, I have no need for that hypothesis. Is that true? I read that somewhere, but just wanted your take on that.
Well, since you mentioned that and you introduced me as a materialist, I would make a slight correction to this. I'm a professional. I'm a hardcore materialist, you might say. Not completely 100% hardcore, but really grounded in the physical principles. Privately, it's a different thing, and many scientists probably are like me. Publicly, they may be proponents of, strict materialism. Privately, they may go to the, synagogue or church or whatever the case may be. And so I don't see actually there is a great divide between these two things. It's just we don't have currently we don't have a framework for even talking about these two things properly. And I hope that you will provide us with this kind of framework for opening a conversation in this direction.
Well, try. Right now, as I'm listening to you speak or anyone speak, uh, right here, I'm seeing an example of non-local correlation or entanglement. In order for you to speak a sentence and for me to hear it and make sense of it, there has to be syntax, grammar, the sequential unfoldment of ideas. Otherwise, you know, uh, the words I'm uttering right now would make no sense. And actually, many people accuse me of that. They say, Deepak speaks word salad. Word salad would be words that are mixed together like a salad and make no sense. But a sentence, any sentence, makes sense because there is a sequence of words. And where is that sequence being orchestrated? Even
Yes,
in language, how do synaptic networks come together in the brain so that you and I can speak a language that you and I can understand? I mean, this is one of the most basic mysteries right here. You can't explain even the experience of speech without somehow invoking some kind of entanglement of ideas.
absolutely. And if I make a comment on this word salad criticism, which I find totally offensive, to be quite honest.
It's okay, I'm used to it.
Oh no, but I think it's completely how shall I uncultured, because I think if you listen to a physicist talk about physics, somebody who is, let's say, a lay person will call it word salad, and if you listen to a lawyer talk about legal issues, it's word
Or
salad.
medical doctor or a medical doctor.
Exactly. So you need to have a particular preparation, background, and understanding to properly appreciate whether it makes sense or not. If it doesn't make sense to you, that means maybe it's your problem.
Second comment, you mentioned tunneling, and I'm asking you this out of curiosity. Is that in a same category as, say, what we call teleportation? As in the metaphor of, say, when you watch science fiction, like um, when
Star
the
Trek.
Star Trek, he says, "Beam me up, Scotty." Is that tunneling?
I don't think so. I don't think it's the same category. It's simply a result of solving the Schrödinger equation. It's with specific boundary conditions. Again, using a physical word salad. Uh, Physicists word. No, it's teleportation is something else. I think it really is over arbitrary distances and in principle creating a quantum state at a different part of the universe. Here, it's just a wave function being a probability, measure
Does
of probability.
teleportation figure in the whole quantum mechanical framework?
I don't think it was initially part and parcel of it. And in fact, initially, quantum mechanics was called wave mechanics because it introduced what you call this duality, particle wave duality, and that was I think initially the physicists that built quantum mechanics, they thought they could kind of patch things up by adding waves. And then eventually it became obvious that patching up classical physics is not going to make it. So yeah, but these things, like the more exotic things like teleportation, I think they came up later on when the principles principles of quantum mechanics were formulated in the Solvay conferences in the 1920s, late 1920s in Brussels. And then later on, people struggled with interpretations. This is one of those problems that that maybe we'll be talking about the
We
interpretation of.
will. I was reading a book actually somewhere here. It's about the whole history of these Solvay conferences. It's called Too Big for a Single Mind. And the book is all the discussions between Schrodinger and Max Planck and Einstein and Niels Bohr. Very fascinating kind of conversations between these guys till they finally came up with the Copenhagen interpretation, which we'll talk about later. But let's get to today's
Sure.
topic. The first problem that you address here, absence of non-linearity and its consequences. So explain what that means, non-linearity, because yes, our normal thinking is linear.
Right. And I have to also give you a sort of personal background because, I started out in sort of quantum mechanical approaches to doing physics. And then there was a period of my life that I switched to nonlinear dynamics and nonlinear dynamical systems. And I noticed this big gulf or divide between these two streams of ideas. And quantum mechanics was born, as I mentioned, in the beginning of 20th century, and it was fortunate to have already had a mathematical edifice built for it a century before. So all the mathematics that was needed to create the postulates of quantum mechanics and then to implement these, the mathematics was present, the Hilbert spaces, the differential equations, the special functions, all of this, Hermitian operators, all of this was available to the more advanced physicists, and they noticed that this is very useful. However, all of quantum mechanics is a linear theory. All these equations are linear. What does it mean? It's a strict proportionality between cause and effect. That is, if you mentioned superposition, superposition is a consequence of it because two solutions of a, let's say, of an equation, Schrodinger equation, or some other equation that you may want to use in quantum mechanics, the Dirac equation for relativistic cases, two good solutions yield a third one, or any infinite number of possible solutions, which are linear combinations of the two, which means you multiply the first solution by some arbitrary number, you multiply the second by another arbitrary number, add them up, and that's a new solution, which is also good. This is linear thinking, and it works in many cases very well, and most of the applications, of course, in quantum mechanics satisfy this, but it breaks down in some cases, especially when you build larger structures. I call it coherent structures. So nonlinearity is opposite to it, not opposite, but a more general version. Namely, cause and effect may not be linear. Maybe in many processes and many situations in the real world, let's say society, economics, finance, linear thinking doesn't work at all. Namely, initially, there could be a kind of ignition process that things go like a wildfire very rapidly. So some people call it the tipping point. You know the book by Malcolm Gladwell, Tipping Point. It's an example of something which is highly nonlinear. A small trigger causes an avalanche of consequences. And you will not find this in quantum mechanics. There's nothing like that in quantum mechanics. Then there is typically kind of a linear gradual increase of whatever you've triggered, and eventually saturation, the process stops. The more input you provide to the system, the less effect you have. It's a saturation. Let's say if you talk about industrial production, you come up with a new product. Initially, people get really excited. They start buying a lot, and then kind of the process stagnates, eventually stops. You produce more of the same product, nobody buys it anymore because it's obsolete. So maybe this is not a quantum process, but definitely is a nonlinear process. And in our society, in modern society, there's almost everything that you observe, from even on the level of human growth, from being a baby, child, adolescence, maturity, old age. It's a process like that, with initial ignition, rapid growth, stabilization of growth, and then saturation and stopping the growth completely. So this is one of those metaphorical examples which show you that there are limits to quantum. This is a problem to quantum thinking, because it's linear in its very foundations. It's not incidental. It's really the basis of it, the mathematical basis. All the equations I mentioned to you, the Schrödinger equation, the Dirac equation, these are linear differential equations, to be specific. In nonlinear dynamics, you have coupled equations with nonlinear coupling interactions. And I think maybe we'll come to it later on in this course, once we develop. Is there a way of salvaging quantum and nonlinear at the same time?
Let me ask you two questions come up. And remember, I'm not a physicist, so some of these questions may seem very naive to you, or even banal, but they're the questions people are likely to ask. Linear thinking is the basis of all algorithms that we use today. Is that true? Linear thinking is...
Yeah, and I would go further. We are almost conditioned to think linearly. I really, quite often when I see projections, prognostication, this is widespread. People believe that what happened a year ago will continue the next year at the same rate. So they say, let's say the population of the Earth is whatever, 8 billion people, and in the next decade it will reach 10, or whatever the number may be. It's based on linear projection. I doubt this will be the case, because these projections break down. So linear thinking is probably built into our mind in some way, because you expect things to continue the way they've been going on until that moment when you start thinking about the future. And so that's one of the fallacies, I think, of built-in biases in our understanding, pattern recognition. So you mentioned algorithms. I think the algorithms, we'll talk about this probably in the future, AI and so on. They basically recognize patterns from the past. They cannot predict future patterns. Maybe we could do a better job by, and let me just be a little bit more specific about this. So we typically look at the rate of growth of something, or rate of change, right? So how fast things are changing. So the projection is, we assume the same rate of change will continue. But if you have more data points, you can calculate this, what's called the second derivative. So the rate of change of the rate of change. And if you do that, you will see that this process is actually saturating, and it will not continue at the same rate, because the second derivative is telling you that it's actually flattening out. So if you take two data points, you connect them by a straight line, that's your linear projection. If you at least three data points can show you that there is actually a curvature in that projection. So that's what I've been trying to communicate to my students when you talk about.
But I was also thinking, as you're speaking, I was thinking of the exponential kind of growth of technologies, So you have, I remember when I first came to this country, I'd never seen a TV set. I saw the TV set for the first time. Then I saw a fax machine. Then somebody said, oh, they're going to be video fax. And then somebody said there's email. Now we have Instagram, this and that. In just the last 30 years, we've seen exponential growth of technology, which defies kind of linear growth.
Exactly. Right? Exactly. So there's one more thing, exponential growth. Of course, it'll eventually saturate, because it has to. And there's always limits to growth. So we have to think about the next step beyond exponential. Well, and there's things which are completely unpredictable in this nonlinear paradigm, which I call it, namely black swan events. breakthroughs or destructive innovations, right, which destroy the previous technology and create a new technology completely. But each time that happens, I think you will see the same or similar pattern of initial ignition, rapid growth, let's say exponential, then linear, and then there is saturation, asymptotic saturation, and then new things happen. And for this reason, I have to make a comment here that there's a lot of negativity in the media in general, right? These days, a lot of negativity. And I think some of the negativity comes from maybe seeing a certain decline or saturation of, let's say, income or whatever the case may be. But this will be replaced by a new paradigm, which will create new opportunities and another exponential period. So for this reason, I'm kind of optimistic, because when negativity kicks in, maybe this is the time to be optimistic. Something good will
As
come.
a theoretical physicist and somebody who's very obviously has to be a good mathematician, does Gödel's theorem kind of fit into this disruption of linear thinking? I recently saw this movie on Ramanujan, the Indian mathematician, called The Man Who Knew Infinity, and he would come up with these theorems which they could never prove, but they were true. So that was a disruption, I would say, in linear thinking. And does quantum mechanics account for, say, Gödel's theorem?
I'm not quite sure about Gödel's theorem and quantum mechanics. I think Gödel's theorem states about the incompleteness of mathematics, so.
It's a
And
disruption in algorithmic thinking, isn't it?
yes, yes. Um, I never thought like that, but you may be right. But I definitely, I saw the movie you're referring to, and I was very impressed, because this is one of these examples that we'll probably discuss later on when we talk about the quantum consciousness aspect of quantum physics, where flash of genius occurs out of nowhere. And this is not, again, this is not a linear thing. You're not building up your knowledge. You just grasp a reality or grab it by the bull by the horns and get instantaneous solution to a problem. And many historical examples are like that. Ramanujan was one of the most prominent and amazing figures in science. But others also came up with these, like Tesla, also had sudden revelations that occurred to him instantaneously, and the solutions were perfect.
Yeah, well, Jack, just this non-linearity raises a lot of questions, which I think we can address when we do quantum biology, because, as a medical student, we learned metabolic pathways. Okay, so there's the Krebs cycle, there's glycolysis, glycogenolysis, and they're all linear examples. But then these metabolic pathways also correlate with each other. They're somehow entangled with each other in order to create homeostasis, and that cannot be accounted in any linear fashion whatsoever.
Absolutely, absolutely, and I think there's more, and I want to mention on this topic that nonlinearity also accounts for things, and you can find this in works of scientists working in nonlinear dynamics, for the creation of structure, let's say, or new structures. That is, quantum mechanics cannot do that. It does not give you the ability to form, let's say, agglomerations of things. It just assumes the existing system, and then you solve the dynamics of evolution in time of the system that you have it. But things like formation of atoms from electrons, protons, and neutrons, you throw them in the bag, and then the atom miraculously is formed. How does it happen? That's one example. Or formation of biological systems out of the soup of elements, amino acids, nucleic acids, phospholipids, blah, 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 things like that. How does that happen? So for this, I think you need the nonlinear paradigm, because that means that there is a phase transition. That's another almost forgotten word. A critical phenomenon in phase transitions are nonlinear phenomena par excellence. because they are these changes of structure, sudden changes of let's say from water to ice. It's a
Or steam, yeah.
Or steam, exactly. And that is a global, almost instantaneous global transformation of a system. Quantum mechanics does not talk about this even, and this happens all around us. I'll just want to do some self promotion, I guess. Many years ago, I collaborated with now deceased colleague of mine, John Dixon, from the University of Warwick in the UK, and we wrote a book published by Oxford University Press called From Non-linearity to Coherence. And this book gives a mathematical path to the formation of new structures from elements. And we actually combined classical thinking with quantum thinking. And very briefly, the envelope, we call it the envelope, the global structure, overall structure of the system was classical, but the ripples on the envelope were quantum excitations. And this may be something that we should discuss in the future a bit deeper, like a hybrid thinking.
Just what you just said brings me to your second point. We've just covered one point, and this is what to do about temperature. So are you referring to decoherence and temperature, which changes a quantum system to what we would call a classical system? Is that what you're talking about?
Yes, that's the flip side of it, right? On the one hand, the classical or lowering the temperature may actually coalesce the system into a coherent structure. Increasing the temperature will decoalesce or decentralize it and destroy quantum coherence. So yes, temperature may play both roles depending on which way you go, depending on the direction of change. But in the context of quantum mechanics, first of all, there is no temperature. In standard quantum mechanics, it's all assumed to be taking place at absolute zero. Later developments in quantum field theory introduced temperature, but you have to remember that temperature is a property of many particles. There is no temperature defined for a single particle. And quantum mechanics was initially developed for several particles, one particle interacting with the field, several particles, an atom, but not for a solid object like this table that I'm looking at right now. So temperature occurs as a result of averaging the kinetic energy of collisions between molecules in a system. So that's how you define temperature, from the movement of many particles. They collide and they exchange their momenta and energy, equilibrate. So temperature only makes sense in equilibrium. That's another thing. And we'll come to it. Biological systems are, by definition, out of equilibrium. So there is a problem on several levels. And then coming back to quantum mechanics and temperature, there are some tricks to include it. But then, of course, you have to think about a quantum system surrounded by a heat reservoir that provides this temperature, so you can define the temperature properly, because for a single particle, you cannot define the temperature.
That leads to many conundrums for me, coming again as a non-expert, because temperature and the arrow of time and entropy and disequilibrium, what you're suggesting, first of all, is there an arrow of time in quantum mechanics? Because if there isn't, then the quantum field, as we see it, is eternal, is timeless, is not in time. And yet it is the loss of temperature, or that leads to the arrow of time, that leads to all these understanding of thermodynamics, is then the appearance of the classical world, in a sense, a loss of order.
Again, yes, very good questions, Deepak. A lot of these questions are open. Some of them can be addressed using sort of more modern approaches to quantum mechanics. Even there is a analog of entropy in the quantum systems by defining something called the density matrix. There are tricks to do that, but of course, this leads us to something which is typically not discussed in the context of biology or consciousness at all, namely quantum mechanics of many body systems. Many systems of many particles. And that is quintessentially what we need to talk about discussing biology, right? Because biology is not a single particle. It's never about a single particle. So there is something along the lines you mentioned. If you go into many body systems, quantum solid state physics, then you introduce quantum degrees of freedom, forming something which is very interesting. I think deserves another maybe hour of discussion, namely collective degrees of freedom. So instead of seeing a single electron or a single proton, now we see an army or a lattice of particles all marching together to the same tune. And that is the collective behavior of quantum systems. And that leads to these quantum excitations. They had different names. The simplest ones would be phonons or vibrations in a solid or crystal, which can also be quantized. And that is a very interesting example as well. But other ones as well, magnons, so spin waves, spin, which is quintessentially quantum, introduced by Wolfgang Pauli into physics and didn't exist before, can form collective oscillations in a magnet. And these in these collective oscillations are also quantized. So there's different levels of quantization, different levels of, and then of course you can turn on the temperature because now you have many particles. Now you can define temperature, but you cannot define temperature for two electrons that are colliding with each other.
As I listen to you, and of course I have my bias, I'm always thinking of an underlying organizing principle, whatever we call that, whether it's consciousness or some kind of field that organizes disparate events into a coherent whole, which is what a biological system is. But I know that we're going to soon run out of time because we have an hour limit on these things. And so what I would like to do is mention some of the other problems. And if you can actually summarize them in one or two sentences, give us a glimpse of what people can, a preview of what they can expect as we announce our course on quantum mechanics, quantum biology, and quantum consciousness. So your third point is open systems and quantum formalism. Please explain what those words mean.
This is probably equally important to the previous problems, maybe even more so, because quantum mechanics typically deals with closed systems. You define the system in physics, and there's a boundary, and then you pretend that nothing interacts with that system, and then you find the system's evolution or energy structure, et cetera, et cetera. Open systems are systems which allow for the particles to flow in and out, fluxes of matter, as well as fluxes of energy. In biology, without fluxes of energy, nutrients, molecules, systems die. There is no biology without the flux. And this is an open system by definition. And there's more, when you open the system to energy, then of course you can create excited states. Excite the system, and like I am now excited, as you can probably see. You can excite the system to a higher energy level, and it's very difficult to predict what will happen next because there is maybe another flux of energy coming in the next millisecond or 20 milliseconds later, like in mitochondria, and so it's very difficult to reconcile this with quantum mechanics, which is typically, in equilibrium. One example where things in physics are somewhat reminiscent to it is laser. When you pump the laser with energy, you go from a lamp-like behavior to coherent light coming out. And that's why some physicists and biophysicists in the past used the laser as an analogy for biological system, quantum biology or quantum consciousness, even our brain.
Actually, one of my, I wouldn't say friends, but somebody that I communicate with occasionally is Brian Josephson, who's about my age now, but he got the Nobel Prize when he was in his 20s for superconductivity.
Josephson Junction.
He's now in Cambridge with the Mind Matter Institute, as he calls it. He has very uh, physicalist views, by the way, on the mind as well. But it's very interesting that he, in those days, in the 70s, was a student of Maharishi Mahesh Yogi along with myself in meditation. And so he has a history of looking at consciousness as well.
Interesting. I met him once many years ago in Tokyo at a conference, and yes, I mean,
I
he's
still
a
communicate with him
legend.
on email, but he's very strong in his opinions.
I see. As one would be, getting a Nobel Prize at the age of 20 something,
Yes. Okay, then you talk about importance of quantum statistics when going beyond few particle interactions.
Exactly.
Is that something to do with this whole cubism and quantum mechanics as it's being?
A little bit. Some of it may lead you there, but the main thing is that, when you go beyond several particles, as I already explained, you have to introduce statistical measures. That is, let's say, properties like specific heat or of solids or susceptibility of magnets, how the system as a whole of many particles responds to external stimuli. And for this, you need statistics. Quantum statistics is different from the classical statistics, and you can see the hallmarks of quantum physics in these systems, which is amazing, and nobody has been talking about it because that would directly apply to biological systems, which are by definition many particles, many molecules, even consciousness. And you will see the hallmarks through averages or fluctuations rather than wave function, because for these large systems, it's not so simple to define the wave function, but it's much simpler to define the response to stimulation. So quantum statistics, Fermi, Dirac, Bose-Einstein, two types. We can talk about it in the next lecture or conversation, let's put it this way.
Absolutely. And so as I'm looking at these other problems you raise, I just want to mention them, muddying the waters with various interpretations of quantum mechanics. Last time I looked on Wikipedia, there were over 30 of these interpretations. But having researched a lot of them, the two most prominent ones still seem to be Copenhagen, the original one, and then the multiverse, which is being favored by Sean Carroll. I interviewed him at length for 3 hours, and he stuck to his guns, and he said there are infinite universes, which also implied that there are infinite versions of you and me. Now, apparently the math is very elegant, and this is the basis for string theories and many other
Let me
ideas.
respond to this with one sentence. I'm a hardcore nuts and bolts physicist, empirical. If something is not measurable, if something is not demonstrated experimentally, it doesn't exist to me. I'm sorry, that's my materialistic approach to it. It could be beautiful mathematics, it could be very elegant, but if there is no demonstration of this veracity, why should I worry about that? For now, anyway, maybe in the future.
But then, Jack, this will raise other questions because the mind is not measurable, nor is consciousness measurable.
Maybe we can define in our conversation some ways of interrogating, at least, or
it's inference.
Yes. I'm not saying that you need to measure consciousness.
I believe that the only direct experience of consciousness is self-awareness, only direct. Everything else is inferential.
Yes.
We can go into that. And then you also talk about quantum mechanics on a macroscopic scale. Are there exceptions to that? I believe that actually it applies on a macroscopic scale, that all objects are quantum mechanical in nature, but the probabilities cancel each other out. So you have what appears to be a stable system, right?
Yes, and again, this harkens back to the idea of this classical envelope and quantum ripples on it. So we should be looking for quantum ripples and not focusing on this so seemingly classical envelope. Let's say this table is looking very solid, but there are quantum excitations in terms of vibrations of the table. If I had sensitive measurement apparatus for it, I would be able to see it.
Other issues that Jack raises here as problems with quantum mechanics include structure formation and quantum phase transitions. We already spoke about quantum phase transitions, but what you're saying is structure emerges as a result of quantum
Exactly,
phase
exactly.
transitions, right?
That's exactly what I mean.
And before the phase transition, there's no structure.
Yes,
It's
yes,
dimensionless.
that's exactly it. And there's a problem because for this you need nonlinear effects. And I told you in the beginning, there's no nonlinearity in quantum mechanics. So for the emergence of structure, you need interactions. Interactions introduce nonlinearity. And okay, that's the problem. But I think it's a solvable problem. It's just maybe not properly formulated yet.
Jack also talks about quantum biology, quantum medicine, talks about quantum psychology, quantum psychopathology, and gifts of quantum thinking, talking about the complexity of the brain, the relationship between brain and mind, and many other phenomena, including extrasensory perception, premonitions, dreams, creative insights. There's a lot to discuss here, but this was a teaser for everyone. And what I would like all of you who are watching this program is to first tell us whether you found this conversation interesting. Secondly, do you want a certification course on quantum mechanics, quantum biology, and quantum consciousness? And thirdly, would you like to introduce in that course question answers, tests, and all of that? Because Jack is an expert. He's a professor of quantum biology. You can see his credentials. He's also an expert in quantum mechanics and mathematics. And I feel very fortunate that he and I have been able to collaborate on this book, Quantum Body, which is enjoying extraordinary support from all of you. So, with that, we'd like to say goodbye today, but we do want your feedback on whether we should do this certification course on quantum mechanics, quantum biology, and quantum consciousness for students of science and technology, for students of philosophy, and for those who want to find meaning and some idea of what the heck is going on. Why are we here? Why is there a universe? How it came to be? Why is there something instead of nothing? Why do we exist? Why is there not just what we call reality, but the awareness of reality? There is something called the universe, but then there is something called the awareness of that. And if there was no awareness of existence, then for all practical purposes, there's no existence. Awareness of existence goes with existence. So give us your feedback. Any last comments, Jack, before we wrap this up?
Yeah, maybe one historical comment. I like to throw them into the mix. About 12 years ago, I was invited to the Indian Institute of Technology in Jodhpur for a conference on quantum biology, and the hosts stated that they want to create a quantum biology course. That was 12 years ago. And I expressed my skepticism, saying that this is too early. We don't know enough. And they said, and it's very difficult, by the way, because you need to know biology and physics. And they said, don't worry, we have about 1 million applicants every year. And even 1% of applicants who would be qualified to enter into a grad school, they will be brilliant geniuses that can easily master this course. Now, 12 years later, I think we can say that probably we can invite the general public to this kind of course or conversation about these topics. The things will clarify for all of us as we discuss them openly.
And I think what you're saying makes a lot of sense, because as we open this discussion to the world, we will get brilliant people helping us evolve this new science of quantum biology and quantum consciousness. Since you mentioned historical, I wanted to uh, quote Schrodinger. I shared with you this quote this morning. My interest in consciousness actually is so inspired by Erwin Schrodinger, without whom we wouldn't have the wave function. And this is what I'd like to read. And this has been my inspiration as well. The Upanishads are the most comprehensive philosophical treatise ever written by man. They are based on an ancient idea as old as Indian thought itself, that the most profound reality is one, and this one is identical with our own self. There's no room for a divided self in the Upanishads, no conflict between our true self and the outer world, no dichotomy between mind and matter. All is one, and we are that one. Schrodinger was particularly interested in the Vedantic concept of Atman, which is the eternal self or reality. He believed that the Atman is identical to the wave function in quantum mechanics, which is a mathematical description of the possible states of a quantum system. Schrodinger wrote, "The very essence of our being is not in an undetermined state, but rather the eternal self." On and on. But the point here is we now have a framework for at least beginning to address the most fundamental questions of our existence. There is existence, there's awareness of existence, and they're somehow connected. So thank you, Jack, for championing this new course. And with your help, we hope to actually engage a lot of people across the world. And as much as we share ideas, I hope we'll learn from them.
With, if I may add, with mutual respect, that is the spiritual aspect as well as the materialistic aspect. I think we're mutually respectful of each other.
Thank you, Jack.